I want to just spend the rest of our time on this section just getting some more practice, doing flux integrals, and using the divergence theorem. Okay, so I've got a new problem on the board. E is the right half of the ball of radius A. Remember, a ball just means a solid sphere. Okay. S is going to be the boundary of E oriented out. Okay. Now, if I say it's the boundary of E, I'm saying it completely encloses E. Now, if E was half of a sphere, the boundary of E, I'm going to sort of draw this so that it's facing us. So I've tilted it towards us a little bit. The boundary of E is going to come in two parts. Because if I just have half of a sphere, that's completely open-ended. That's not the boundary of anything. I'm going to need to cap it with a plane. A portion of a plane, rather. I'm going to have this disk that will essentially be in the xz plane. So I'm going to have S1 equals the right half of the sphere, and S2 equals a disk of radius A in the xz plane. Okay. So two surfaces there. Okay. My vector field F is y. Okay. We're going to calculate the flux of F across S two different ways. Okay. Remember, I like to ask this sort of question, so we'll get some practice. One is by evaluating the appropriate surface integral, or as we've just discussed, surface integrals. So that would be the flux across S1 and the flux across S2. Okay. And the second way is by evaluating an appropriate triple integral. That, of course, is going to be using the divergence theorem. Now, for this problem, if I just said to calculate the flux of F across S, there's no way I would want to do it as the surface integrals. I would absolutely want to go to the divergence theorem and just do a single triple integral. But just so we get plenty of practice, we're going to actually do it both ways. Okay. Now, what I'm going to suggest is that you pause the video and try to work it out. Try to work it out both ways. When you come back, I'll give you the answer. If you got the same answer both ways, and you feel good about that, there's really no need to watch the rest of the video. You're certainly welcome to, but if you want to just move on and work on the homework and get caught up in other things, that's a totally reasonable choice to make. But if you struggle with this, or if you don't get the right answer, or if you just feel like you'd feel more confident working through it together, then you can certainly watch the rest of the video. But right now, go away, okay, and try working this out. Try working it out both ways. See if you can get the same answer both ways. Okay. Welcome back. Okay. Hopefully, you did get the same answer both ways. And the answer that you should have gotten is 2/3 pi times a cubed. Okay. A is the radius of the sphere, and since I didn't give you a specific number, we're just going to have an A in our answer. Okay. If you got that answer both ways, fabulous. Okay. If not, or if you just feel like you'd be more confident if we work through it together, stick around. What I'm going to do in this video is evaluate it what I think is the simpler way, evaluate the triple integral by using the divergence theorem, and then in the next video, we'll do the two surface integrals. Okay. So, if I'm going to evaluate this using the divergence theorem, I'm going to need to know what the divergence of F is. So the divergence of F is just del dotted with F. So that's the partial with respect to x of the function in the first component, plus the partial with respect to y of the function in the second component, plus the partial with respect to z of the function in the third component. They all happen to be y. Okay. But when I take the partial with respect to x, I just get 0. When I take the partial with respect to y, I get 1. And when I take the partial with respect to z, I get 0. So the divergence is just 1. That's lovely, because the divergence is constant. Okay. So I can say the flux is, by the divergence theorem, the triple integral along E of 1 dV. But if I'm integrating 1, that's just going to be the volume of E And remember, if the volume of a sphere shows up in the context of a larger problem, and I didn't explicitly say calculate this volume by evaluating an integral, you can just use the geometric formula. So, because it was half of a sphere, it's going to be 1/2 of 4/3 pi times the radius cubed, but that's going to be 2/3 pi times a cubed. So that's the answer that we should get. I'm pretty confident there weren't a whole lot of places to make careless errors in this particular calculation. So I feel pretty confident that that's correct. In the next video, we're going to come back and we're going to evaluate the flux, but by doing it as the two surface integrals. Okay, see you then.